Hello everyone. So myself Rajesh again here with another interesting as well as important topic in thermodynamics. So we are going to learn the first law of thermodynamics today. We have already learned zeroth law and the corresponding property which is defined from zeroth law of thermodynamics temperature. Now here in the previous lecture we have hinted about first law of thermodynamics and we have defined various modes of energy transfer and we have discussed about work transfer and PdV work. Now you are in a position to understand first law of thermodynamics and its mathematical expression and its importance in both closed system as well as open systems. So straight away we'll move on to the lessons. So all of you are aware of the law of conservation of energy principle, right? It states that energy can be neither created nor destroyed, but it can change its form from one to another. That is the law of conservation of energy. So, first law of thermodynamics is stated or evolved from the energy conservation principle. So, from the experiments of the scientist Joule, you know what Joule's law is, right? So, this is a statement evolved out from the Joule's experiment in general, which is noted as the statement for first law of thermodynamics for all adiabatic processes. What do you mean by adiabatic process? A process in which there is no heat transfer. There is no heat transfer across the boundary between two specified states of a closed system. So there is no energy, only energy transfer. There is no mass transfer. That is what meant by a closed system. So for any adiabatic process taking place in a closed system between two states, initial and final state, the net work done is the same regardless of the nature of the closed system and the details of the process. Irrespective of the process or nature of the closed system, the net work done is the same because there is no heat transfer. Mass transfer is already not there since it is closed system. So net work done is the same. That's what is stated as per first law of thermodynamics, and it is based on the consensus arrived at from the Joule's experiments. So in order to find out or write down an expression, mathematical expression in general for first law of thermodynamics, you need to consider a system moving relative to a reference plane. As I have shown here, this is a reference plane, okay, where the height is 0, z is denoted as 0. Z represents the height or the measure of potential energy, and v is the measure of velocity, is the measure of kinetic energy. Okay, so this point cm stands for center of mass. Okay, this red rectangular box indicates the system, and some energy is going in and some energy is going out. Both are shown with different arrows. Red shows the energy going in and blue arrow shows the energy going out, and the center of mass moving with a velocity v. Okay, now for the system shown above, the conservation of energy principle or first law of thermodynamics is expressed as, you know, that it is nothing but the expression of conservation of energy. So net energy transfer, the amount of energy going in minus amount of energy going out, is equivalent to net energy change. So suppose 100 kilojoules of energy going into a system and only 50 kilojoules is coming out of the system. So 100 minus 50 kilojoules. So 50 kilojoules will be stored inside the system in some form. It may cause change in internal energy or it may transfer as heat. We don't know. That we will analyze later. But still, the total amount of energy will remain the same. So here it is stated the amount of energy going in minus amount of energy going out will be stored within the system. E in minus E out is equal to delta E. Delta E is a change of energy, final energy minus initial energy. It may be negative or positive depending on the process. Delta E could be negative or positive depending on the process. Fine. If the system is having a lot of amount of energy in it, some amount of energy is given to the system, so the energy out might be larger, isn't it? So delta E may be negative. Now the total energy of the system, E of the system, is not delta E. E of the system is a sum of, you know, that sum of internal energy, kinetic energy and potential energy. We have seen in the previous sessions. Now kinetic energy, it is half mv square, and potential energy is mgh or mgz, right? Now the change in stored energy of the system, that is delta E, is equivalent to change in internal energy plus change in kinetic energy plus change in potential energy. Therefore, we can substitute for delta E here. E in minus E out is equal to delta E, you know. So delta E is substituted as delta U plus delta KE plus delta PE. Change in internal, kinetic and potential energies is equivalent to the total amount of energy, net amount of energy coming in minus going out. So if the system does not move, potential energy will be there, but kinetic energy will be 0. Again, if the system is situated on the reference plane, okay, z is equal to 0, so potential energy also would be 0. Therefore, we can say E in minus E out is equal to delta E. E in minus E out is equal to delta U. It is called a stationary closed system. So for a stationary closed system, change in energy will be equivalent to change in internal energy. I think we have already seen that this one in the previous class. Now, the mechanisms of energy transfer differ in open and closed systems. In open system, there could be three kinds of energy transfer across the boundary: heat, work and mass. But closed system, only heat and work. So mass flow is restricted in the case of a closed system, but mass flow could happen in the case of open system. So mass flow is another form of energy. It is flowing mass. Mass carries certain amount of energy. Mass flow carries certain amount of energy, so that would be considered as an energy form. So in an open system, any of these three types or a combination of these three or any one or two could happen depending on the process. In a closed system, only heat and work, because mass entry is restricted or prohibited, we can say. Only the working medium can expand or compress within the confined space. For example, a piston cylinder device where a certain amount of gas, certain mass of gas is contained. When heat is given, it will be expanded, then some work will be taken out, then the piston will come down and it will get compressed. Right, heat will be rejected. So work transfer and heat transfer will be taking place. But in the case of open system, like turbine or a compressor or a nozzle, certain mass will be coming in and certain mass will be going out. So mass flow is there, and it can be insulated so that it can become an adiabatic process. So in that case, there won't be any heat transfer, but still work transfer will be there in the case of a turbine or a compressor. But in the case of nozzle, there won't be any work transfer, only the mass transfer will be there. I hope it is clear. So energy transfer mechanisms in open system are threefold, and in closed system only 2 out of the 3 in open system will be available. Fine. So heat transfer is represented by Q12 in a process, W12 for work transfer, mass flow is denoted by M. So generally, while by considering all the three forms of energy transfer for a general system, we can write down the change in energy E in minus E out is equal to Q in minus Q out plus W in minus W out plus energy in the form of mass flow in minus energy in the form of mass flow out. That is equal to delta E, change in energy of the system. So more compactly, if you write, you can write like this. Delta E represents change in internal kinetic, potential, etc., etc., etc. So much forms of energy. So, or on a rate form, that is per second, per unit time. Per unit time, if you want to write, you may have to put a dot on each and every term. If you put a dot on top of each and every term, it will become a rate form, that is per unit time. So for constant rates, the total quantities during the time interval delta t are related like this. Q is equal to Q dot into delta t, W is equal to W dot into delta t, and delta E is equal to delta E into delta t in kilojoules. Okay, when multiplied with time, kilowatts will become kilojoules. Watts is joules per second. So per unit mass basis, you can write the energy balance. Lowercase e is used for specific energy. It is commonly known as specific energy per unit mass. Energy, total energy per unit mass is termed as specific energy. So you can write like this, kilojoules per kilogram. Now for a cycle, the net heat transfer is equal to net work transfer. Net heat transfer in a cyclic process is equal to net work transfer. So we can write like this, Q net is equal to W net. Q net is equal to W net for a cycle, because the change in internal energy will get cancelled out. So if you have any questions or doubts or clarifications, please comment below, and your feedbacks are always welcome. If you have any specific questions or topics to be included in my lecture series, I would like to get requests from you so that I can include that in the future lessons. Please subscribe to my channel to get notifications on the newly uploaded videos. Please keep watching and stay learned and educate others by sharing the links. Thank you so much. Have a good day.